Okay, we're finishing up chapter 24 now. This will go pretty quickly. Section K is probabilities using permutations and combinations. I've already really discussed how to do this in prior videos. We'll just do a few more examples here. In the prior videos, we saw, I think the examples I showed were with tree diagrams. So technically, you could solve any problem from this section using tree diagrams. The thing is, the tree diagrams might be absolutely massive. So that's why I really recommend when the sample spaces are going to be huge, use combination theory. And then section L is Bayes' theorem. I've said in just about every video in this series so far, I've commented that I think that section's dumb. I stand by that. We'll see when we get to it. Just a reminder, permutations involve ordering objects, combinations don't. Let's do one. So here we go. We're going to choose 7 out of a squad of 12. There are 12 people, including a captain and a vice captain. So it's those two plus 10 more. I want to choose a team of 7 using both the captain and the vice captain. All right, so I could start doing a tree diagram here. My first pick might include one of those two, or it might not. And then assuming that I chose one of them, then there'd be one of them left over, but I might also not take that, so that'd be 10 over 11 here, and then assuming I've taken both of them, then I guess there's none out of 10 left, and my 10 out of 10 for the rest. Okay, but then I gotta also consider, well, what if I chose one of them here, but then I didn't on my second branch, so then there'd still be 1 out of 10 remaining who was the other of the captain or the vice captain, and then there'd be 9 out of 10 remaining who weren't. But then I need to consider, well, if I didn't take it, then there'd be 1 out of 9 remaining who was, and then 8 out of 9 remaining who weren't, and so on. And you can see this tree is going to be really large for me to consider all of the possible branches where I could end up getting both the captain and the vice captain. Because of course my first 5 choices might even be not choosing them. And then I might choose them for the last 2. So this tree is going to be huge. I refuse. I'm not going to do it. Let's do it the smart way. If I want to choose both of them, so there are 2 people who are either the captain or the vice captain, and I want to choose both of them. And there are 10 people left over, and I want to choose 5 of them to make 7, right? 5 and 2 make 7. And then the total number of ways that I could choose 7 people out of the 12 is, well, that's 12. Choose 7. And that's pretty much it. You grab a calculator and you've got yourself an answer. The next problem, this is probably one of my favorite ones in the entire textbook just because of how like morbid it is, and I'm a terrible person. Like, why do we have a problem in a math textbook about a plane crashing and people dying in it? It's like this, who wrote this? They should be fired. Anyway, so there's 22 people on the plane. 3 of them happen to be professional golfers. The plane crashes. 4 people die. Please let the golfers have survived. Find the probability that all 3 of them live. Okay. So thinking of, let's flip this around. Let's think about who dies. So let's make this even darker, right? So of the 3 golfers, I want none of them to die. And of the 19 other people, sorry, but I want 4 of you to have perished. And in total, there were 22 people, and 4 of them are going to have died. So we calculate this, and we get 0.530. Could I have thought about survivors instead of people who died? Yes, however, this is the IB we're talking about, so we always need to keep in mind efficiency, and notice that here and here I would have had to have typed 2 extra buttons on my calculator in performing this calculation, and people, time is of the essence, so we got to do this as fast as possible. That's why I chose the top method instead of the bottom, but of course they're going to get you the same answer. We know combinations are symmetrical. N choose R is always equal to N choose n minus r. So yes, clearly those two are going to be the same. Next one, let's do one with permutations. Okay, so we've got 6 people who are going to be randomly seated on chairs. So I mean, first of all, my denominator, I know it's going to be 6 factorial. Right, that's how many orderings we have. Now, specifically though, we want A, B, and C to be seated together. So how are we going to do that? Well, first of all, for A, B, and C seated together, if we think about them as a single unit, they themselves are going to have 3 factorial orderings. And then if we think about inserting that single unit and ordering it in with the other 3 people, so people, D, E, and F, that's kind of like 4 individuals that we need to arrange. So we end up multiplying that by 4 factorial. And we calculate that. I forgot to do it, but whatever that is the answer to this problem. And that brings us to Bayes' theorem. So here's what the book has to tell us about it. Probability of A given B. We've talked about that before, right? The probability of A given B should be equal to the probability of A and B over the probability of B. How does that compare to what we see before us here? Well, the denominators are the same. The numerator is slightly different. Why is that? Well, the probability of B given A multiplied by the probability of A, that is the probability of A and B. We talked about that in the last video very briefly. We know that if they're independent events, if B and A were independent, then the probability of A and B would just be the product of their individual probabilities. But if they are not independent, if they're dependent, then this is one way of expressing that. We have the probability of A, and then we're going to multiply by the probability of B given A. And again, notice that this formula is completely symmetrical, right? We could swap some things around. We could put this in the numerator. We could put this in the denominator over there, and then we'd get probability of B given A is equal to probability of A given B times probability of B divided by probability of A. Okay, great. Let me erase some of that mess. What's happening down below? Probability of B is equal to all this. Well, I think that makes sense, right? So, again, assuming that A and B are dependent here. So A is either going to happen or it's going to not happen. So we've got A or not A. And then depending upon whether A happens or doesn't happen, that's going to then change the probability of B given A happening or not happening. So either A happens, and then we're going to multiply by the probability of B given A having happened, or A didn't happen, and then we'll multiply by the probability of B given that A did not happen. These two put together need to give me the probability of B, because there's no other situation that could have occurred. Either A happened or it didn't happen. And then again, based on that result, we're able to calculate the probability of B. That's a mouthful, but take a moment to think about it. It makes sense. Now let's look at what the IB formula book gives us for Bayes' theorem. It's essentially the same. I'm going to show you the top row of this first. So first of all, notice the IB formula has switched A and B comparatively to the textbook. That's okay. And then their denominator, rather than using probability of A in this case, they are using the expanded form. So that's what they've got there. And now, to make things worse, they give you this here too. What's going on there? Well, okay. So originally when I was explaining what was happening up here, I said either A happens or A doesn't happen. Well, what if A was not like a binomial event? What if, for example, like we could be talking about whether a child is a student in a high school or not. So that could be A or not A. But we could also reframe the question. We could say, well, the student is either a freshman or a sophomore or a junior or a senior or not a student in high school. So we can break up that event A, or again, down here, we're talking about the event B, into case 1, case 2, case 3, we could really expand it beyond that. However, if you check the IB syllabus, which I will show you, they tell us right down here that Bayes' theorem for a maximum of 3 events is what we need to be able to use. Now, I think this is stupid. This formula, to me, is needlessly complicated. If you like this, awesome. But I don't think you should need to do it this way. We can use a tree diagram. I'll show you an example. Here's a previous IB problem. Take a moment to read it. Okay. If I'm going to do this, I'm going to use the method on the left. I'm just going to make a tree diagram. Okay, I can fill in the probability that she takes a car, the probability that she bikes, the probability that she walks, and then I can fill in the probability that she's late or on time in each of those situations. And then using techniques we saw in a previous video, I could calculate the probability that she rode her bicycle given that she was on time. So that's what I would do. And again, that would be like taking this product plus this product plus this product. That's going to be my denominator. And then my numerator is going to be the probability that she rode a bicycle and was on time. So that's going to be just this product here. So we see that is my numerator, and then we see all 3 of them together, or my denominator. We talked about that in a previous video. But you could technically calculate all of this using, here, this is the Bayes' theorem method. I don't know. I don't get it. I don't see why anyone would want to do this. So I would not do anything in that box. And notice the mark scheme says we're either doing this tree diagram or we're doing this, and then we're getting here. So regardless of which method you choose, you're going to end up with this calculation, and then you'll solve it, and then you're done. So that's Bayes' theorem. Don't worry about it. Just it's a tree diagram problem. And that's it for chapter 24. There's a lot more to be said about probability. I think I might put out another video kind of briefly discussing some of my favorite applications of probability. One is called Buffon's needle, which has you drop a needle infinitely many times, or finitely many times, but a sufficiently large value. And depending upon where it lands in a particular region on the ground, you can actually get an estimate for pi out of that. And that's cool. That involves some calculus as well. And then I have, there's a few beautiful paradoxes out there. Simpson's paradox, very famous. The birthday problem and the Monty Hall problem, those two are probably the 2 most famous probability problems in the world. In fact, anytime, if you Google right now, the most famous probability problem ever, it'll be either the birthday problem or the Monty Hall problem. Depending on how you phrase your question, you could probably get one or the other. And then, but my favorite paradox is this one where you know that a person has a boy born on a particular day. What's the probability that the other child is a girl? And in fact, knowing that the child was born on a specific day changes the probability of the other one being a girl. That one just blew my mind, but that's a really great problem. Anyway, I'm not going to put that in this video. That'll go in its own one. But that's all like extracurricular stuff. We don't need to know that for the B. Given that you watched this video, I hope that you enjoyed it and learned something. Take care.